One of the few things every human on this planet, and every other living thing for that matter, shares is the fact that everything gets 1,440 minutes per day. Our planet makes one rotation on its axis, the sun comes up, the sun goes down, and we start the dance all over again. Part of the human experience is how we spend that time. Multiple sources, including the Mayo Clinic and the World Health Organization, suggest humans need 7 to 10 hours of sleep. The average workday is also 7 to 10 hours, depending on where you live. The time in between can be consumed with breaks from work or between classes, meals, getting ready for the day, and getting ready for bed, not to mention time spent commuting to and from work or school. If you have children, they take most of the rest of your time. With only a few precious minutes per day to ourselves under the best of circumstances, what would an additional 30 of those minutes mean to us? How could Microchip Technology help to create a time machine to give us this part of our lives back? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Dr. Mark Smith. Mark is a senior marketing manager at Microchip Technology, working out of the mixed signal and linear device business unit. Welcome, Mark.
Welcome. Thank you. Thank you for having me on here.
Thanks for joining us on Beyond the Microchip. In the intro, we briefly talked about how precious and fleeting time can be and how we never seem to have enough of it. You found a novel solution to this problem and got some of your day back. Tell us about it.
Okay. Well, it kind of highlighted itself recently on one of my family vacation.
Yeah.
I was on a surf trip. And whenever you go on surf trips, the goal is to get good waves. Oh, man. And the waves were pumping. They were really pumping, meaning that they were good. They're perfect, nice size. And we wanted to get out early in the morning. And that's the best time when you wake up, you want to get out there when the waves are at their peak, and so you can take advantage of it. But I also want to get a cup of espresso. So, and one of the things that, but fixing espresso is an art form. I wanted a good cup. I'm on vacation. I want both surf and a cup of espresso that I did.
We're not talking about a regular cup of coffee.
No, this is a good cup, that you do. And so they had an espresso maker there. And at my house, I have a way of getting great espresso. We'll talk about that, about getting my day back. But I didn't have it on this trip. And so I went to the kitchen area because it was a surf camp and they had an espresso maker there. And so I ground my beans and I put them into the portafilter and then I put it into the machine, and I realized that it needed to be heated up because to get good, you got to wait for this thing to heat up. And good machines take about 30 minutes, but I said, okay, I'll just live with it right now.
We're talking almost 200 degrees, right?
Oh, yeah, it needs to get up to, exactly. Yeah. To get up to the proper temperature on espresso at 200 degrees is a good number. Some people do a little lower. Some people go a little higher. It depends a little bit on the beans and so on. Yeah. So anyway, it wasn't at the right temperature. So I pushed the start button, and this machine was set up so that it's not going to, once you hit the start button, if it's not at the right temperature, because it was at room temperature at this time, you would have to, it's going to wait, it's going to heat up, and then it gets to the right temperature. Then it starts to pull the espresso out. And I said, so I started sitting there and I go, but the waves are pumping, so I'm just not going to wait and to get my cup of espresso. So I pushed that button, and I had to go get my stuff ready. I had to get my surfboard, my rash guard, my surf wax, my sunscreen, get ready so I can go out and hit the waves. And so I went away, and I went and got busy, and I forgot that I'd pushed that button on the espresso maker. And I go, oh man, this is about 5-10 minutes later. I come back, and sure enough, the espresso got to the right temperature and dispensed it. But it was overflowing that cup of coffee. You see, at home, I have an espresso maker that I don't have to remember to turn it off. It shuts off perfectly. So I was so used to this time machine we're going to talk about that I forgotten I had this overflowing cup of espresso. And so I had two choices. I either make another cup or get out in the surf. And so surfing was more important than espresso.
You had to make a choice.
Yeah, I had to make a choice. And I didn't want to make that choice, but I did. And it wasn't a very good cup of espresso, but the surf was great. So that highlighted itself that next time I need to bring my espresso maker on my next surf trip.
So let's get into that now. So espresso you don't just grind beans and filter water through it like a regular cup of coffee. An espresso is a process. Can you walk us through the process of espresso?
It's more than a process. It's really an art form because, believe it or not, every cup of espresso, there are so many parameters to get to the taste that comes out of espresso, and a lot of parameters. You really need to be, in order to get that good cup that you're looking for, the goal is to really control these parameters you're talking about. I mean, you're right. The basics are you're pumping water, hot water, over these coffee grinds, and you're pulling oils off of the coffee, and those oils, along with the water, go into your cup of espresso. And the goal is to get a good one is you got to figure out, the pressure that you're pushing the water through, the temperature that you're at, the amount that you're at, how fast you're doing it. All these change the type of oils that are coming off and how quickly those oils are coming off of the coffee beans that are there, and that changes your taste. And actually, a couple examples. If the first oils coming off the espresso beans are actually pretty sour tasting, okay? Then the next, so like the first few seconds, and then the next little bit, it actually becomes sweeter in taste, okay? And then eventually, after a while, like on a long shot or something, it starts to become bitter. And then you have this mix of flavors. Now in your cup, you're gonna have all three of those.
Right.
And the goal is to have them at the right amount and temperature so that when they get mixed together, you get this nice cup.
So can you game it where you get like 1% larger than the others?
And so most of it, you could do that, but usually people do is they'll just push it. When you push this cup of espresso, you'd like that espresso to come out 25 to 30 seconds to do 60 milliliters, which is a double shot of espresso. And if you've done your grinds at the right grind level, okay, and you've tampered it correctly, you're going to have a nice tasting cup of espresso that's not too bitter, not too sour, but just perfect.
Just right.
Just right. Now, anyway, that's the kind of the art form of doing espresso. And there's books being written on this. There's podcasters that talk about this. So I'm not an expert. I'm just a hobbyist. I kind of like to geek out a little bit on this stuff.
Well, so that's what we want to talk about today. So we talk about, we often hear things like you can't have it all, when the reality is you probably can, but you can't have it all at once. So what you figured out is a very novel solution to what could be considered a regular household item, right? The espresso machine.
That's right.
And for most people out there that drink coffee is you grind the beans, you place it in a filter, you fill a container full of water, and a programmable coffee machine is you hit the button for 6 a.m., you walk away.
Right.
When you come in at 6:10, there's a whole carafe of coffee waiting for you. That's what I did this morning before I came in. Yeah. But I'm not as into it, or I should say maybe I don't appreciate the finer elements of this art form we're talking about. So you wanted to take this approach to your espresso maker.
That's right.
You went one step further. Where'd you begin?
Yeah. The real problem is that it takes about a half hour every day to do what I've talked about with a off-the-shelf, I call a single boiler, maybe an entry-level espresso that can do good espresso. And by the way, the espresso I'm talking about is going to be better than you can get at any coffee shop. I mean, usually I come and I taste at a coffee shop. Now, I have espressos all over the world and stuff in coffee shops in my neighborhood, and they're okay. But I like the one at my house better.
Right.
So, but you can do it with an entry-level machine. It takes about a half hour. Right. And my goal was, and what does this half hour entail? Okay. You want to get that coffee, you need to get the machine warmed up And a lot of it's the machine warming up, getting nice and warm. You want to be able to then, when you press that espresso and the stuff cup, the water comes out, that the temperature is consistent and consistent at a right temperature. And then you go through the tamping, and you also in the grinding of the beans. But those are the two. Heat it up for a while, constant temperature. And then if you're going to walk away or something like this, you want to be able to have it automatically shut off, and a few other neat stuff. But the time saving is that you want to turn it on at the right time before you need your cup, and then it be ready and nice and warm and at a constant temperature to be able to do that. So
right, and shut itself off.
Because
that was what you were dealing with, was the overflow, right? So we're dealing with pressure, we're dealing with time, we're dealing with temperature, and then there's also the interface and the preparatory work, and then the afterwards.
Yeah.
So when you built your magic machine, where did you begin first? What was the first thing you wanted to fix?
First thing I wanted to do was temperature.
Okay.
And because you get an entry-level machine comes out, and temperature it's done with thermostats. And thermostat is two pieces of metal, bimetallic switch that it gets to the right temperature, and these open up. And then when it gets cooled down again, those two pieces of metal come back together, and that turns on and off the heater. The problem is that when you're trying to get to the exact degree when you're pulling your espresso, these thermostats have about a 40-degree range that they're on or off. And so you're kind of guessing.
It's quite a delta, yeah.
And so sometimes you might be at 240 degrees Fahrenheit. Sometimes you're down at 200 degrees. And so you have burnt coffee.
It's quite a margin of error.
It's cool, it's cold. And so you're never sure when you pull the espresso, am I at the right temperature? And then of course, then you're looking for the best shots every day in the morning. And so anyway, so the first thing I did was I changed that out. I put a thermocouple in it, a thermocouple controlled device. And then, when you add a thermocouple, it's not that simple. You got to hook it into a little mini computer. And I used a Linux-based mini computer using Raspberry Pi that runs it. And then controls it within 1 degree. And so on. And using, if you look at coffee machines, these espresso makers, they say PID control. And that's what I did. Effectively, I was doing that, but I did it kind of on my little Raspberry Pi and stuff to get to that temperature level. That's for advanced machines. And I'm talking this is this entry-level machine that I had.
So we got the temperature dialed in.
Yeah.
What happened next?
So then, of course, I would wake up in the morning and go, the best way to make sure my machine is nice and warm, as soon as I wake up, I turn on this coffee maker and the espresso maker, get it warmed up. So by the time I want that cup, it's all nice and warm and ready. The issue is that that worked great when I was kind of analyzing and studying and how to hook up this temperature monitor and stuff. But, you wake up, you've got to run downstairs, turn the machine on, run back, then get all ready for work. And that worked for a little while until you forget. You wake up, you're super busy, you are ready to go out the door, and then you realize, I want a cup of espresso, but I forgot to turn this thing on. I'll use a subpar amount. I still got to wait around. I'm not going to have my nice cup every day. So
when it gets to temperature, you've got that locked in. You've got your tiny margin of error. But then you got to get the water to temperature, and that's a significant time challenge.
That's the time challenge. And so I said, okay, let me see what things can we do. I can put it on a timer like you talked about in your coffee maker. You do the timer. But I said, I got a little mini computer here, and machine learning's all around this AI. How do we do it? And so I said, okay, let's think of how it could just follow me, and I don't have to think about it. It just turns it on when it needs to. And so a little research online and figured out about time series analysis. And so right now, the next step was to design it so that it would turn on and get to the right temperatures and when it anticipated I needed that cup of espresso.
So it's learning you.
It's learning me.
Right.
And so the idea would be, if I put it on a timer like you talked about at 6:30, that's great. But what about the weekends? Okay. Or what if my work schedule changes and I'm super busy, maybe super early, or other times it's a little bit later. So I wanted to learn my pattern and not have to think about it, and then be able to go ahead and have that espresso done. So I built a machine learning algorithm around it. But I wanted to see how good that machine learning algorithm was, right? I wanted to check it out. So it has a self-grading algorithm. It tests to see how good it is, right? And right now, I just checked it yesterday, 79.5% of the time that I want an espresso, it's already warmed and ready to go. About, 4/5 of the time. I'm
right.
ready.
So people at home can't see it, but you're monitoring it right now.
Yeah, I can monitor from my cell phone right now. It's a little mini computer, so I can add it has a web page on it, and I can do that. I can see what the temperatures, I can see what the water level is. We'll talk about that in a second, and it can measure shot times associated with it. But one of the big features is that when I need a cup of espresso, when is it ready? Is it nice and warm and ready to go so I can get that cup? And about 80% of the time. And it's really cool because, if I have a histogram on it that kind of talks about my history, but most of the time I have a cup in the morning, but sometimes I'll have a cup of espresso in the afternoon or in the evening, especially on a weekend or something like this when, you do it. And sure enough, it's ready. So that was the kind of the journey on, getting this cup of, this machine that was, that knew when I needed the cup. And that worked really well. One other thing that I added to it is that, once again, time saving and stuff. So when I wake up, do it. One other problem I came up about is that I'd forget to put water into it because there's a water tank. And so it would do the cup and wouldn't pull out a cup of espresso. And so I added a water tank sensor to it that measured accurately the water tank level. And using an inductive position sensing technique, which is pretty cool technique. And it's super accurate. So now you wonder, that doesn't really care for a water tank because, all you need is to know at what point you need to restart, refill that water tank. But since at work, I work with inductive sensors, I kind of did an overkill. But the side benefit of that was that it's now accurate enough to measure the espresso that comes out in my little cup. So I can, when I press the button, I don't even have to turn it off. It measures 60 milliliters or whatever I've programmed and then shuts off. It's accurate within just plus or minus 5 milliliters. So using this water tank sensor that I added into it. So.
Yes, for those of you keeping score at home, we're now 1 degree plus or minus, and we're now exactly at 60 milliliters.
And 60 milliliters.
Okay.
And a web page that tells me the shot times, and you want it like 25 to 30 seconds. And usually why is that? That's just a rule of thumb that people have kind of learned, that I've learned, gives a good cup of espresso coming out. But some people might do 20 seconds or some might do 35. And they want to get that feedback by, if I can pull it a little longer, then I need to tamper it. Maybe I need a little finer grind of coffee so that it would go a little longer, or a coarser grind of coffee so that it'll be a little less. And then that gets tunes, or it's the art form of coming out with that consistent cup of espresso.
Where did the Nixie tube come in?
Yeah. So, it's because, having wires around a piece of kitchen gear and wires and computers around a kitchen gear would not fly for my partner, my wife, in bringing it into the house. It would not fly.
I think those of us that are married can relate.
So I wanted to bring this into the house and have it, somewhere in the kitchen or nearby. And so I needed to make sure that everything was buttoned up together and looked good. And so instead of having the wires, I put them all into a 3D case. But on the front, You can use my cell phone and I can look up the web page, but I wanted an indicator that kind of told me a lot of stuff about what was going on without having to go to the web page. And so I added this, it's called a linear Nixie tube bar graph display. So Nixie tubes are kind of some older technology invented in the 50s, and it's pretty retro looking, but it looked pretty cool. It hangs off the front of my machine, and it's a bar graph, and it does several things. One, it just tells me the water level of what's in the tank, so I know when to do it. But it'll also tell me the temperature, too. If I push the button and it's not the right temperature, it tells how soon it will get to that temperature.
Ooh, okay.
It also tells me when it does an espresso, it then tells me the water level of the espresso. So it tells me how close I'm getting to an end for the espresso. So it gives me some feedback there. And then it also tells me when some alarm systems, like if I'm need more water, it starts flashing at me and stuff like that. So the goal was to have a kind of a retro looking display that I could add that looked okay and that passed, the aesthetics requirements of the household, so I could bring it in and use it every day in the kitchen.
So it's kind of like a dashboard that just gives you status of everything?
That's right.
Okay.
Yep. Yeah, so it's fun.
So we've got inductive sensors, and we've got thermocouples, and we've got mini computers, and we've got a web page. Any other technology that you've brought into it?
Yeah, machine learning, but we added that that was part of your mini computer. It's machine learning, so that was good. And I think that's oh. These are the big parts. Those are the big parts.
All right, and we do this every day.
Every day. So I wake up and get to go downstairs and, I have a nice cup before I go out the door. Sometimes I'm running out the door and I bring my cup with me. So it's good.
So I'm doing some back of the envelope math here while you're talking. We're talking about 30 minutes a day that you've effectively eliminated. That comes out to about 780 hours a year, which gives you, calculate 30.
Oh, wow.
30 minutes a day. That gives you 210 minutes a week. Yeah, that gives you about 7.5 days of your year back. So you've effectively bought a week of your life back, which is half of most people's vacations that you just got back.
I like that. That's good. I didn't realize that.
So I'm thinking about this now. So you've leveraged technology in such a way that not only do you get a perfect espresso, that's exactly the way you want it.
Right.
You've taught it to learn you instead of the other way around with most interactions of consumer technology is you've got to figure the thing out and do what it wants. It's figured out what you want. And on top of that, you bought back a week of your life every year.
Pretty good. Pretty good. I like that. 10 years, that's going to be a long time.
Yeah,
right?
do a calculation on that one. And you get to go out and catch the break.
And yes, when surf's up, I don't have to worry about and I can bring my espresso, out to the break.
You can bring it with you?
Yeah, I can bring it with me, right? And that's 1 minute to fix.
What's not to like?
Half hour.
So we're talking about inductive sensors and thermocouples. So what can you tell us about those things as a technology? Why are they useful?
Yeah, okay. So I'll start with thermocouples. Thermocouples are great for measuring temperatures accurately. And, what is it? It's really measuring the voltage across two dissimilar metals. And what you do is you put those two dissimilar metals in a high temperature environment, and thermocouple is great. They're used, thermocouple temperature measurements are used in lots of industrial applications. Your ovens are going to have them, but a lot of industrial applications over a wide range of temperatures. It's super good. And so you have these two dissimilar metals that are right next to each other and in a high temperature environment, and they'll create a voltage but a really small voltage.
Right.
And so then you use that, you need to convert that into a temperature. And so that was one of the technologies we used. And at Microchip, we have a very nice IC family called the MCP 960X family that will convert this metal voltage. They call it a temperature EMF, but it's a voltage, and convert it into a temperature that comes out and through an I2C port that can be read right into a mini computer or to a microcontroller. And so all I had to do, I had to put that MCP onto my little proto board or circuit board, and then run a thermocouple, which are these two dissimilar metals, up to my my boiler to measure the temperature. So that was one of the technologies I used, and it was the advantage was this IC does all the calculations of that voltage, because that voltage will change over temperature that we talked about, and it does the calculations for you for a given type of thermocouple.
Right. What about inductive sensors?
Yeah, and so inductive is a really great technology that Microchip has, and it's called inductive position. I like to call it inductive position sensing, and it's a position sensor that measures the location of a target. And it uses magnetic fields to do that, but it doesn't use a magnet. Traditional magnetic field sensors have used Hall effect type sensors. They call it Hall effect because it's detecting this magnetic field. Ours don't use it. Instead, we use a piece of metal as the target. And this piece of metal, now in the sensor, is actually traces on a PCB board. And those traces on this PCB board create a magnetic field, and then the piece of metal disturbs that magnetic field at a given location. And we've set up the sensor to have a primary and a couple secondary receive coils, and we can zero in, triangulate where that position of that piece of metal that's moving is. And so for the water tank, what happened was that in order to do the water tank sensor, I put a float that was floating inside the water, and right at the top of wherever the water is floating, and that float had a piece of metal on it. It has copper on it.
Okay,
a really thin piece of copper, and then outside the tank, I had my PCB board, which is my linear sensor that is generating a magnetic field, and then that float disturbs that magnetic field, and I'm able to accurately figure out its position. And the technology is not just for water sensors. In fact, it's really good in a lot of industrial applications that need to measure angle or linear position, or your automotive applications that need to do, angle or linear position. It can handle really high temperatures, and it's accurate over high temperatures. So it's a neat technology. In fact, it's a really good technology. And we at Microchip we have a family, and one of the parts is called the LX3302 family of inductive position sensors that use this technology. If you're driving around in a car today, there's a chance that your car accelerator pedal has a couple of inductive position sensors in there. Now, you may understand why a couple. And the reason is because for automotive, safety is pretty important. Accelerator pedals pretty important. If something happens and one of the systems breaks down, you want to have a backup. Redundancy. And so for safety critical applications, many systems have redundancy.
So the inductive position sensor would measure how much you're pushing on the pedal to translate how much power goes to the engine.
Exactly. And that's just one of many places. You can chassis sensor, your rotor position inside a motor, your gears within a transmission. These can all use inductive position sensing.
Okay, so we've got automotive, we've got industrial. Suppose one of our listeners at home has a use case for this technology in one of those areas or in a different area.
Yeah.
Where would they go? How could they adopt it?
Yeah, I mean, best place for these technologies, both of these, is come to our Microchip website. In fact, I think in our show links we'll put a link down. I can give you a link that you can see where they can go and learn about inductive position sensing. And there is Thermocouple ICs. Just even searching Thermocouple ICs on our Microchip website will come up our family. That's I would say the best place to go for it. One other place, I know we're talking about, white goods and, coffee makers, and just one other application for inductive, which is really nice, is kind of industrial level knobs. And the neat thing about it is that for an inductive position sensor, you could build a knob that is on a piece of glass and the glass is not cut. Normally a knob has some sort of shaft that goes through the glass. Well, you don't have to with inductive. You can actually have the metal on one side of the glass, maybe glued, has a kind of a mount point that's glued on that glass. On the back side, you can have a sensor. So your ovens or cooktop.
Yep.
And on the back, you can have the sensor. And you now don't have to drill in the glass. And so the cost of drilling is often a fairly expensive manufacturing step. You can save that cost with using inductive. So that was just one other, since we were talking about, stuff in the kitchen.
Because now we're getting into consumer appliances.
Yeah,
okay.
that's
all right. So let's see. We got microchip.com/inductive-position-sensors. So it's microchip.com/inductive position sensors with a hyphen in between each of those words. And then for thermocoupling, we've got microchip.com/thermocouple-IC. Those are two places you can go and check that out. And of course, anywhere on microchip.com, we have a search button. You can get to find anything you're looking for in a search field. So you said this is not a new technology. It's been around a while, but it's obviously is going places. We're talking about non-contact through glass.
That's right.
Do you have any predictions on the future of the technology?
Where
are we going with it?
Right, especially with inductive, both of them are good. They'll be around, and thermocouples has been around forever. But inductive position sensing is a technology that will be, in my opinion, replacing traditional or older Hall effects technologies because of three big advantages. One, it's more accurate over temperature. The magnetic properties of a magnet will change with temperature. And with inductive, the techniques we use at Microchip don't change with temperature. The other one is immunity to stray magnetic fields. In industrial applications and electric vehicle applications specifically, the amount of magnetic fields with electric motors is getting higher and higher, or charging currents gets higher and higher. And the inductive position sensing can reject that. We have active rejecting of those noises. And the other one is we just don't need the magnets themselves. So we can get rid of the magnet, save cost there. You get a slightly bigger PCB board because the sensor does need PCB board to be the sensor. Right. But in general, I see this transitioning into the getting away from Hall effects into inductive is the future. As new designs, we're seeing this already in the automotive industry, and we will, I see that as new designs come up, they're going to go, okay, well, I can do it with Hall effect, I can do it with inductive. They'll make the decisions, and I see them choosing inductive over and over. So I see that happening.
Yeah, I've seen that in the automotive application set, specifically around climate control. A lot of automakers are now putting knobs back into the interface because when you're trying to deal with sliders and digital to figure out how to make it cooler or warmer, that's a safety hazard.
Yeah.
So it's nice to have a tactile knob that you can actually use.
Yeah, they're liking knobs now, and knobs are good, and we can use that with inductive for sure.
Any final thoughts?
I enjoyed this, of course, is a hobby. So, I enjoy doing it. So anyway, it's fun to talk about it. This idea of machine learning and AI, I think the idea is it's good and it makes us more efficient. And I think ultimately, though, how does it improve our lifestyle and letting us do stuff that we want to do, right? And I think if it's allowing us to do stuff that we want to do, I think it's the right direction. So sometimes you go off on tangents with AI and stuff, and maybe it's not allowing you to do stuff that you want to do. And anyway, this was kind of fun thing that allowed me to do what I wanted to do. Right?
Gives you your life back, right?
Yeah, exactly.
Yeah. In business, I think there's three immutable laws. One is how can you raise revenue? How can you decrease costs? But the third one is what I would call a time machine. How do you get your time back? Yeah. Since we only have so much of it. Dr. Mark Smith is a senior marketing manager at Microchip Technology, specializes in mixed signal and linear devices, as well as where to find a nice point break. He joins us here at our global headquarters in Chandler, Arizona. Mark, thanks for joining us.
Thank you for having me.
Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience. Where is your favorite surf spot?
So I live in Southern California. So the place I go is a place called Salt Creek.
Salt Creek?
Yeah. And so
Big long hill you got to walk down, right?
down, yeah. It's a nice place. And then Trestles is good. Trestles is, Lower Trestles is the best in Southern California. And
A lot of mythology around Trestles that I'm aware of. Yeah.
So, but I go to Salt Creek a lot.